This is Andrea Hendricks. Let's continue the study of section 5.1 dealing with inverse functions and looking at the homework problems from this section. So I've selected number 3 from my math lab. It asks us to consider the graph of y is equal to the cube root of x minus 3 and determine if it's 1 to 1. Well, all we have to do is determine if it passes the horizontal line test, and in this case it does. Any horizontal line only crosses one point of the graph, so yes, this is a one-to-one function. Determine whether the function is one-to-one. If it is, find a formula for its inverse. Couple ways we could do this. We could enter this on the graphing calculator. If we enter it on the graphing calculator and graph that function, what we're going to find is something that looks like this, which is not one-to-one because it does not pass the horizontal line test. Another way you could do it is find two values, a and b, and show that if a is not equal to b, let me back up. Our whole definition is that if f of a is equal to f of b, then that must show that a is equal to b. Well, if we have two output values that's the same, that came from two different input values, then it's not one-to-one. For instance, if x is equal to 6 or x is equal to negative 6, let's look to see what happens. If x is equal to 6, y would be the opposite of the square root of 36 minus 6 squared, which is 36 minus 36, or 0. Well, if y is or x is equal to negative 6, notice that we'll get the same thing. So therefore we have two different x values that have the same y value, and so that contradicts the definition of a one-to-one function. Find a formula for the inverse. Well, if it is not one-to-one, then it cannot have an inverse function. Number 7, determine whether the function is one-to-one. Yeah, that's a cubic function, right? It's got a stretch and moving up, so it is one-to-one. And if so, find the inverse. Well, if y is equal to 3x cubed plus 6, what can we do to find the inverse? Well, we would have to interchange the x and the y, right? And then solve for y. So we would have x minus 6 is equal to 3y cubed. Then we can divide through by 3. And then we can take the cube root. So the cube root of x minus 6 over 3 would be the inverse function. Number 8 says the function f of x, which is equal to 2 to the x, which we'll study in the next section in more detail, is one-to-one. Find the following values. Well, it doesn't really matter if you know that that is an exponential function. To find f of 0, we would do 2 to the 0, but we know anything to the 0 power is 1. Well, by definition of the inverse function, what does f inverse of 1 have to be? Well, if f is a number or the operation that took 0 to 1, then f inverse has to be the operation that takes 1 back to 0. So f inverse of 1 has to be 0. Now, number 9 says to determine if the pair of functions are inverses of each other. Are these functions inverses? Well, if we look at the line y is equal to x, then the function and its inverse should be symmetrical with respect to the origin. And that definitely looks to be true. We can test a few points if you want. Like, for instance, this looks to be like 4, 0, and 0, negative 1. And on the inverse function, this would have to be interchanged. 0, 4, and negative 1, 0. So yes, those are inverses. Choose a graph that shows a graph of a one-to-one function and its inverse. So that would be ones that are symmetrical with respect to the line y is equal to x. Okay, clearly this one is not. To be symmetrical with respect to the line y equals x means if you fold the graphs along that, they would be mirror images. And so far we can see that none of those would be. But what about this last one here? Yeah, if we fold along y equals x, we do get a mirror image. So this is the one we would need. Now we have f of x is negative 2 over x and g of x is negative 2 over x. We've got to find g composed with f. So g composed with f would mean to do g of f of x, which is g of negative 2 over x. Now to do g of negative 2 over x means we're going to replace the x with this negative 2 over x in our function g. So function g is negative 2 over x, but in place of x we're putting negative 2 over x. Kind of weird, huh? And so to divide means to multiply by the reciprocal, which would be negative 2 times x over negative 2. But those divide out, just giving us x. The next part of this was to find f composed with g, so f of g of x is actually going to be the exact same thing, right? Because f of g of x, we're plugging the same function into the same function, and we get x. So remember what happens. If g composed with f and f composed with g are both x, that means that f and g are inverses of each other. Graph the inverse of the function f of x equals 4/3 x minus 2. So one thing you can do if you want to find the inverse yourself and then think about what the graph would need to look like, we can do that. If we interchange x and y, oops, didn't mean to say plus 2 there, and then solve for y, we would get x minus 2, x plus 2 is equal to 4/3 y. And then we can multiply through by 3 over 4. So 3 over 4 times x plus 2 would be equal to y, which would be 3/4 x plus 3/4 times 2 would actually be, what, 6 over 4 or 3 over 2? Okay. So just remember the things that we're talking about with lines. To graph lines, this has a y-intercept of negative 2, a slope of 4/3. This has a y-intercept of 3/2, a slope of 3 over 4. So they both have positive slopes, so they're both increasing. One has a negative y-intercept, the other one has a positive y-intercept. So we can ignore B and C right away because those contradict the fact that the slopes are both positive. Sorry about that. Apologize. So what we would need then is the one that has the slope of 4/3 and negative 2 and a slope of 3/2, or y-intercept of 3/2 and a slope of 3/4. But also it has to be what? When they're inverses of each other, they have to be symmetrical with respect to the line y equals x. And you notice that's the only one right here that's happening. We draw that line y equals x and fold it over. Those are a mirror image of each other. So we have found our answer, part D, and that's what we need. For the function f of x equals 3 over x, determine whether f is 1 to 1. If so, find a formula, and then give the inverse, the domain, and range. Okay, so what we need to find out first is this 1 to 1. Well, yeah, 3 over x is a translation of, actually a stretch of 1 over x, so it would look like this. So it is a 1 to 1 function. Find a formula for the inverse, so we would say if y is equal to 3 over x, and then we interchange x and y. And now we need to solve for y. We multiply by, cross multiply by the LCD, or just cross multiply, we would get yx is equal to 3. So to solve for y, we would get y is equal to 3 over x. Okay, so this is its own inverse function. So f inverse of x is equal to 3 over x. What is the domain and range? Well, the domain is all values except for 0 in the denominator, right? And the range is actually the same thing because it has a horizontal asymptote at 0. Okay. And the graph, obviously, the function and its inverse are the same, so that's fine, right? Because if we draw the line y equals x through there, it's a mirror image of itself. Number 17, if the function is 1 to 1, find its inverse. Well, we know that the square root of x plus 5 looks like this, so that is 1 to 1. So to find its inverse, we would say y is equal to the square root of x plus 5. Then we interchange the role of x and y. So to eliminate the square root, we have to square. So we would get x squared is equal to y plus 5. So x squared minus 5 would be equal to y. So our f inverse function is x squared minus 5. Now you have to be careful with this particular one because x squared minus 5 is a whole parabola, which is not 1 to 1. The inverse of this function, if we draw the line y equals x, we should get something that looks like this. Okay, only a half parabola. So what we got to think about are the domains and the restrictions on those. So we know that the square root of x plus 5 is defined for values of x that are what? Greater than or equal to negative 5, and in that case y is greater than or equal to 0. So when we interchange x and y, this becomes y is greater than or equal to negative 5, and x is greater than or equal to 0. So our inverse function is only defined where x is greater than or equal to 0. Find the inverse of the function x minus 9 squared for x greater than or equal to 9. So this is one where x is greater than or equal to 9 is only this piece, right? We've ignored the part to the left of the vertex. And so we would say y is equal to x minus 9 squared is defined for x greater than or equal to 9, and we know y is greater than or equal to 0. So we would take the square root, well, I'm sorry, first we have to interchange x and y. And in doing that, changes the relationship of the domain and range to get y is greater than or equal to 9 and x is greater than or equal to 0. So now taking the square root gives us the square root of x is equal to what? Just y minus 9. And then we can add 9 to get y. So f inverse of x is equal to the square root of x plus 9, but only defined where x is greater than or equal to 0. Okay. Now, I've selected a few problems from the book just to go through briefly. It says in number 25, explain why a polynomial function of even degree cannot be 1 to 1. Would you remember what even degree means? Even degree means that at the end it's either going both up or both down. And because of that, your function is not going to be 1 to 1 because the end behavior is the same. Explain why in some cases a polynomial function of odd degree is not 1 to 1. Well, when it's odd degree, all we know is that the end behavior is opposite. In between there, it can actually repeat the y values, right? And so that would not be 1 to 1. And then these just concept checks real quickly we'll talk about. For a function to have an inverse, it must be 1 to 1. For a function f to be of the type mentioned in number 27, if a does not equal b, then we know that f of a cannot equal f of b. If f and g are inverses, then f composed with g of x is equal to x, and also g composed with f of x is equal to x. The domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. If the point AB lies on the graph of f and f has an inverse, then the point BA lies on the graph of f inverse. If f of x is equal to x, Then for any function, f composed with g of x is equal to g composed with f of x, which is equal to x. Right, the identity function is its own inverse because the value of x doesn't get changed through the identity. If a function f has an inverse, then the graph of f inverse may be obtained by reflecting the graph of f across a line with the equation y equals x. If a function f has an inverse and f of negative 3 is equal to 6, then f inverse of 6 has to be negative 3, right? The inverse is what takes you back to the input that you started with. If f of negative 4 is equal to 16 and f of 4 is equal to 16, then f does not have an inverse because it is not 1 to 1. Right? We can't have two different input values giving us the same y value. If f is a function that has an inverse and the graph of f lies completely within the second quadrant, then the graph of f inverse lies completely within the blank quadrant. Well, we can kind of think about this. Let's say that here's our function. It's all in the second quadrant. To do the reflection, what's going to happen? Whenever we fold it along the line y is equal to x, it's going to lie completely in Okay, let me think about how that's going to be. Should be completely in the second quadrant. Okay? I'm sorry, I said second. I meant third. Okay. And you can play around with that on the calculator. No biggie if you can't figure that one out right away. And then just a few more. Use the definition of inverse functions to show analytically that f and g are inverses. So all I want you to understand here is that whenever it says solve analytically or show analytically, you've got to find f composed with g and g composed with f. And they both must equal x if they are inverses of one another. Okay? So like number 38, if we had f composed with g of x, we would do f of x minus 3 over 4, which is 4 times our input, x minus 3 over 4, plus 3. So that would simplify to be x minus 3 plus 3, which is just simply x. And then you would also have to do g composed with f of x. Okay. So that would be g of x minus 3 over 4. But here, to plug in, no, I'm sorry. What is f? F is 4x plus 3. So g of 4x plus 3 would be 4x plus 3 minus 3 over 4, right? Our input has to take the place of x. And so that's just 4x over 4 because the 3's are eliminated, and divide up by 4 gives us just, oh my goodness, you guys have to bear with me today. I'm sorry, I'm going on little sleep. My little one was up last night. Okay, let f of x equal x cubed and evaluate each expression. Well, we know what f of 2 would be. F of 2 is 2 cubed, which would be 8. F of 0, 0 cubed is 0. F of negative 2 would be negative 8. Then f inverse of 8 would mean what x value took us to the output value of 8, which would be 2. F inverse of 0 is what we need to go back to what we started with. And f inverse of negative 8 would be negative 2, right? The graph of f is shown below. Use the graph to find each value. F inverse of 4. So what we're trying to figure out here is what value of x took us to the y value of 4, okay? And then f inverse is going to be that value of x that took us to the value of 4. So here we go. So it looks to be like 4, 4 is the point on the graph. So if the x value of 4 took us to the y value of 4 under f, then f inverse of 4 would be that value 4. F inverse of 2, well, it kind of looks like 3. Would you agree? Really approximating there. So f inverse of 2 means to find out what value of x had the output value of 2, and that looks like 3. So f inverse of 2 would be 3. Okay. And another way to think about it, if the point AB is on the graph of f, right, then for f inverse, that interchanges. So f inverse of b then would be that value of a. That's another way you can think about it. Now, indicate whether these screens suggest that y1 and y2 are inverses. So I just wanted to look at this for a minute. Notice on the 91, x and y1, if x has an input value of 1, the output is 6, and then 3, 8, negative 4, 1, and so on. So we see these ordered pairs are on the graph of y1, and so on. On the inverse function, we would expect to see 6, 1, 8, 3, 1, negative 4, 14, 9, and so on. And do we see that here? Yeah, we have 6, 1, 8, 3, 1, negative 4. So yes, these are inverses. Okay. Notice here, number 92, they're not, because on the y1 we have 1, 7, but over here we have 7, negative 1. So these are not inverses. And then the last screen I want to talk about is graph the inverse of each one-to-one function, where all you're given is the graph. Well, to graph the inverse, you're going to interchange the x and y values, right? So for instance, if you know on 94 we have the point 1, 0, and we also have the point 2, negative 1. We also have the point, trying to find a more precise point, what is that, negative 1, 2, 3, negative 3, 3. Okay, so when we're graphing the inverse function, we need to interchange the x and y. So we're going to have a point, instead of 1, 0, we would have 0, 1. Okay. Instead of 2, negative 1, we're going to have a negative 1, 2. Instead of negative 3, 3, we're going to have a 3, negative 3. Okay. And we also know that it has to be symmetric with respect to the line y is equal to x. Okay. So if you can envision folding this over, and it might even help to get a few more points if you want to, but envision folding this line over. Okay, if we fold this over, flip it over, it's going to look something like this. Okay, and that would be the graph of the inverse function. Okay, that concludes it. I know you're thinking enough already. Okay, but hopefully you understand that concept of inverse functions. If you have any questions, please don't hesitate to contact me. Thanks.